Hello and welcome everyone. My name is Stefan and I will guide you through some of the tools and services here at EODC that allow users to discover and access EO data. I would like to start with a simple question. Say I want to study this area here, Lake Wörthersee, using satellite data. How would I go about it? So 5 years ago, this meant navigating through complex portals, downloading raw data from Copernicus hubs, and parsing metadata in XML formats. At EODC, we supported this through a CSW server accessible via a client called EOMX. EOMX was simple to use, and you could roughly define a study area and period. The results you got were a list of file paths which you would use with the access to our storage system from your virtual machine. The CSW server, which was primarily used to distribute raw Copernicus Sentinel data, unaltered and exactly as downloaded from the respective data hubs, is still operational today, and some of our long-term customers still rely on it. But it is no longer our main focus. Today, we use STAC, which is a modern web-native specification for EO data cataloging. STAC, in its core, is very simple, it's flexible, and it is built on JSON. STAC defines a few core concepts. So there is an item which represents a single spatiotemporal feature, like a Sentinel-1 scene, for instance. There are assets, which are describing the locations of the actual files, geotiffs, metadata XMLs, thumbnails, and so on. Then there's the catalog, which organizes collections and items. Similarly, there is a collection specification, which builds upon the catalog specification. And this represents a group of related items with shared metadata and spatiotemporal features. The STAC API is a REST API specified in OpenAPI, and it follows the OGC API features specification to search for STAC items, using, for instance, properties like cloud coverage or other product-specific metadata. STAC also supports extensions, which are modular add-ons that describe the specific types of data better. For instance, there's the SAR extension, which adds fields for radar-specific data, the EO extension for optical data, the PROJ extension for coordinate reference systems, and so on. STAC, and more specifically, the STAC API, also powers the EODC portal, which we'll explore in just a minute. However, before we switch, it is good to understand why a web-native design like STAC is useful, actually. Coming back here to Google Maps, we see roads, buildings, and so on, and features that would easily allow us to explore this region. Now, the vision behind the cloud-native geospatial data and these initiatives like STAC is to make it just as easy to explore EO data as you would do to search restaurants in Google Maps. Let's now switch to the EODC portal, which is available at portal.services.eodc.eu. The EODC portal is the central entry point to EODC data and service offerings. At the top, you'll see 5 main menu items. Explore, which opens an interactive web map for browsing datasets. Data catalog, which is a searchable list of all available collections. Gallery, which showcases applications and use cases. In documentation, you find technical guides, tutorials, and API references. And in services, you will find an overview of EODC service offerings. Okay, let's click on Data Catalog. This is where we can browse all the available STAC collections, similar to what many users might already know from the STAC Browser. You will see datasets like Sentinel-1 DRD, Sentinel-2 L2A, the Copernicus DEM, and more. Let's search, for instance, for gamma and select the gamma node collection. This is a calibrated backscatter product derived from Sentinel-1 GRD data. It was processed at EODC using the processing software Wizard. Now, this already illustrates an important difference to a previous CSW-based catalog. At EODC, we now use STAC to expose not just raw data, but also value-added products like this gamma node backscatter, CEOS-ready ARD NRB datasets, and more. Some are in cloud-optimized formats like COGS, cloud-optimized GTIFs, or other native formats. Some are freely accessible, while others require authentication or license acceptance. Back on the collection page, we see a description of the dataset, metadata fields like spatial and temporal extent, fields that are used by certain STAC extension, for instance, spectral bands used by the EO extension, and a link to the raw JSON metadata. Let's open that JSON. There you will see fields like ID, type, providers, extent, and links. This is the actual STAC collection object, and it's what powers the portal interface. Okay, back on the catalog, let's now click on Launch in Explorer. This opens the interactive map viewer with the gamma node collection preloaded. Currently, the portal supports filtering by spatial and temporal properties, but we are also working on expanding this to include metadata fields like platform, orbit direction, and cloud cover. Spatial filtering is automatically applied as you pan and zoom the map. Coming back to our example about the Wörthersee, let's zoom in and see what kind of data from the current collection is available there. On the bottom, we can also retrieve a code snippet which we can copy and paste into our programming environment and which gives us the same search results in a programmatic manner. We will look into this in a moment. Now let's click on a single item and explore what we can find there. On the left, we see the item's metadata and the item's assets. What is presented here is just another view on the STAC item itself, and it includes all kinds of properties like date time or the WK2 projection information. In the metadata, we also find a link to the original STAC item, which is again a simple JSON returned by the STAC API. Let's click on it and have a look at it now. This provides the full metadata available for this item. The section named Properties contains all the item's properties, including basic information like the date time, but also some extension-specific information like orbit states. We also see, for instance, that this item provides multiple assets. There's an image in VH polarization, one in VV polarization, and some metadata files. Also note here that each asset has an href, which is either a public HTTP link or a local VM path. Or, as we see here in this example, it can also be both if we make use of a STAC API extension called alternate assets. Back on the Explorer, let's try to see if we can visualize this item too. Next to the thumbnail, we will find a little map symbol, which we are going to click now. Thanks to the cloud-native format of the data, what you see on the map here is not just a preview, it is the actual data. It's rendered live using a service called ttiler. If you're interested in how this works, we will learn more about ttiler in our next technical webinar. As you can see, we can zoom in and look at the image in great detail, and it's easy to navigate and display on the map. Like with the collection before, we can now look at a code snippet for accessing this particular item in Python. The Explorer provides a button that gives you ready-to-use code snippets. So let's copy this and move over to our JupyterLab environment. In this cell where it says copy and paste code for data access, we will do exactly that. It loads the STAC item and opens one of its assets, in that case, the VH polarization band. So let's execute this cell now. This loads the VH band as an xarray data array using Rio xarray. The href points to the actual data file, which is cloud optimized and ready for streaming. We can now work with the data in Python. For instance, we can analyze the distribution of backscatter values in this image. Let's execute the cell. We apply some data processing steps like masking out no data values and plot the histogram. We can also calculate the 2nd and 98th percentiles, which we'll use for visualization in the next step. This histogram gives us a sense of the data distribution. The percentiles help us clip extreme values and enhance contrast when visualizing. In this case, we'll use suggested Vmin and Vmax values in the next step. So now let's visualize the data on an interactive map using a tool called Volume. We will reproject the raster to WGS84, downsample it for performance, normalize the values, and apply our custom EODC color map. This map shows the actual backscatter data styled with our custom EODC color map. Thanks to the cloud-native format and tools like Rio xarray and Volume, we can go from purely metadata to interactive visualization in just a few lines of code. Now that we have visualized a single item, let's go back to the discovery step and see how we can search for items programmatically using the STAC API. Just like before, we can copy the code snippet directly from the Explorer. This time we are using a CQL2 JSON filter to define our area of interest and that time range. This query returns items from the gamma naught collection that intersects our area of interest and fall within the specified time range. We are using the sintersects and any interacts operators to filter spatially and temporally. We can now count the number of items that match our search criteria. If we want to refine our search, we can make use of the CQL query language directly. For instance, we can add a filter for orbit direction. In this case, we only want descending passes. This kind of metadata filter is very easy to use and is quite powerful, and it can be applied to many other fields like cloud cover for Sentinel-2, processing level, or polarization. We see that the number of matching items is now less than before, as expected. That concludes our Python demo. We have seen how to load and visualize a single item, analyze rastered values and apply a custom color map, search for items using spatial, temporal, and metadata filters, and how to count and compare results using the CQL2 JSON language. Finally, let us now switch to QGIS. In recent versions, you can connect to STAC APIs directly. previous versions required the installation of the STAC API Browser plugin. Let us first create a new project and add OpenStreetMap as a base map. Now let us focus again on our study area, the Wörthersee region. We want to connect to the EODC STAC API and load the Gamma Node data as before. To do so, we go to Layer, Add Layer from STAC Catalog. As you can see, we have already configured the EODC STAC API as a valid connection. All you need to do is to add a valid STAC API endpoint and give it a name. Some catalogs require or support authentication. This is not needed at the moment for EODC. Now we can connect to the catalog by clicking Connect. We are being presented with the same list of collections as with any other STAC client. Okay, let's zoom in just a little bit more. We want to get our Gamma Node data again, so we click Filters. In QGIS, we can make use of the current map extent as a spatial filter by clicking this button. To find only the relevant items from our Gamma Node collection, we deselect all collections and type Gamma and select our desired collection. After clicking OK, we see the matching results. We will pick an item and right-click on it to see what we can do now. As you can see, we can zoom to the extent of the item, add certain assets to the map, or even download all assets. We only want to add one asset now. Let's use VV in this case. Again, this data is directly obtained from the HTTP servers without having any download steps in between. As before, we can customize our image using the EODC color map by clicking Properties, Symbology, Single Band Pseudocolor. I will not go into more details about this now, but I want to demonstrate how easy it is to work with the data directly. As a final step, we can now combine our Gamma Node dataset with some orthophotos to provide an additional context to the project. Like before, we go to Add Layers and search for orthophotos in this case. We deselect the Gamma Node collection, type orthophotos, and select all collections and click OK. Let's zoom in again a little bit more and filter for the current extent. Then we can select matching items and add them as new layers to our map. After specifying how the coordinate transformations shall be performed, we already see the photo laid over the Gamma Node map perfectly. Let's add another photo. Okay, with this I want to close. To summarize, we have explored the evolution from CSW to STAC at EODC. We used the EODC portal to browse and explore STAC collections. We accessed data programmatically using Python, and we visualized and analyzed data in QGIS. Thank you for your attention.